Okay, so here we are in our LabVIEW program, and what you're seeing here is the front panel of the program. Each LabVIEW program has two sections, or two windows. One is the front panel, which is what you see here, and the other one is the block diagram. The front panel is kind of the user interface of the program. It's where the user can put inputs and controls, and where they see outputs, which can be in the form of numbers or graphs or images, and a lot of other things as well. But in this program, we only have those three. So now I'm going to quickly show you the block diagram, and then we'll come back to the front panel. So here's the block diagram, and what we're going to do is we're going to zoom out so you can see the whole thing. So we go down here to navigation window, open it up, and so here is our entire block diagram. As you can see, it's kind of hard to follow if you don't know what's going on, and it's definitely a lot more complicated than the front panel, which is kind of the way it's meant to be, because this is where the actual programming happens. So I'll just walk you through this really quick. So in this portion right over here, this is called a DAC assistant. This is kind of the thing that gathers the data from the DAC box and the module that converts the analog to digital. Okay, and then down here, okay, then here is where we're converting strain to force. And I'm going to walk through this in detail a little later in a separate video. So we convert it to force, and then we get the force, and then we convert that to maximum normal stress, maximum shear stress, maximum strain, and maximum deflection. Okay, and I'm going through this really quick, but I'll go through it a little bit in more depth later. And so in this portion, pretty much this entire thing here is the alert system. And then, so for each of these systems, they each have to do with a particular case. So one of these is deflection, maybe normal stress, shear stress, and strain. Okay, so those are kind of the overall alert system areas over here. And down here is where we can write all the measurements to a file. And this part is where we are showing the model. So this is where the image is being called to be displayed. And so I'll explain this a little more later. So now we're going to go back to the front panel and walk you through that. So we go Window, Show Front Panel, and then we're back here. And so here's the front panel again. And so here is kind of the main portion of the program. Here is where you make your specifications. So here where you input the dimensions of the beam and the location of the strain gauges. So right now our base of the beam is 1 inch, and so on and so forth. And here are the various locations of the strain gauges, with the X value being measured from the fixed end of the beam and the Y value being measured from the center of the beam. So as you can see, it's half of the height, either positive or negative, depending on whether it's on the top or bottom of the beam. And so here we have to input the modulus of elasticity of whatever material we're using in our beam. So for our project, we used A36 steel, which is 29,000 kips for the Young's modulus, but we want to put that in PSI, so we have consistent units. In this portion is where we put the constraints. So whatever the allowable maximum deflection is, normal stress, and so on, this is where we specify those numbers. And we can also input a safety factor to just make it safer. So if you're not familiar with the safety factor, it basically just divides all these numbers by this number. So right now, the true allowable maximum deflection is really 0.1, because it's going to be 0.2 divided by 2. Okay, and so in the front panel, anything that has a white or a blank white background is an input, and anything that has kind of a gray or a darker background is an output. So here are kind of controls and specifications, and here are going to be numbers that LabVIEW is telling us. So as you'll see when I run the program, it's hooked up to the apparatus right now. You're going to see all these numbers start streaming in. And so as I apply a deflection, you're going to see right here that it's going to increase. Okay. And the reason you see they're kind of fluctuating a little bit, even though I'm not changing it, it's just there's just a little noise. Okay, and it's not too much. As you can see, the strain is really close, and this is in micro strains. And so, I mean, it's within 1 microstrain all the time, so it's not too much noise. Okay, so I'm going to stop that. Down here you can see graphs of the force and deflection versus time, and since they're linearly related to each other, they're going to behave in the same manner and follow kind of the same path. So as I apply a force, you're going to see right over here the force graph increase pretty immediately. And I'm going to let it down. And also on the deflection graph, you're going to see a similar thing, since they're, again, linearly related. Okay, so I'm going to let it back down. So you can see down here. And in this portion, you can specify where you'd like the data to be written to if you want to export it out. So right now it's set up to export to an Excel file, and that file is going to have 9 columns. And they're specified in the block diagram as to which column corresponds to which measurement. And so if we want to write to file, whatever numbers are occurring right here, are going to be written to the file. And so I'm going to write the file, and then whenever I want it to stop, I just click it again, it'll stop, and it's going to tell me where that file is, so I don't have to go searching for it later. And now we're going to go down a little bit in the front panel to the modeling portion of our program. In this portion of the program, we're going to see an image of the beam and the stress distributions along it, corresponding to this color scheme over here. So little to no stress is blue, and as you can see right now, I'm going to turn the modeling on, so we're going to see what this. So right now there's basically no deflection being applied, maybe a little minimal one. It's going to tell us what the maximum stress is, and then so as I apply a deflection, you're going to see the stress distribution change along the beam. And so as I'm doing this, I'm going to start going a little bit faster, and as you can see, it keeps up with my motion. There's another video that shows this much better, but you can see it's very fast, and it gives a really good picture of what's actually happening. So now I'm just going to turn this off, just to kind of save the program. Okay, and also down here, it's going to show you where the image that's being called is coming from, or what the name of the image is, basically. Okay, and up here, see, you could see how I was fluctuating the beam right here. So I was going up and down fairly fast, right here as well. Okay, so now we're going to go up here, and this portion, the specifications for alert system, is where you specify how you want to be notified of the change, if it's or if your constraints are met or gone above. So here is where you so the way this works is the program needs access to an email account. So right now I just have it set up to access my USC account. So I just gave it my email, my password, and the server that it needs. And here is where you specify, like, to who is going to get the alert text message. And so you select their carrier. Right now I have it set up for 4 carriers: T-Mobile, AT&T, Verizon, and Sprint. That should cover just about anyone. And you can input your phone number. So pretty much any phone number that has those 4 carriers can be alerted with this system. And so right now I just have my phone number in there. And this is going to be the subject of the text message that you get. So we can change it to something else if we want, but right now just have this system alert. And so right now the alert system is off, which is good, because if let's apply maximum deflection of greater than 0.1. So right now it's greater than 0.1, and we didn't get any alert messages, which is good because it's off. So now I'm going to put it back down a little bit. So now it's below 0.1. So when I turn this on, it's not going to give us a message right away. But right after I go above 0.1, we're going to get a message on the screen, and I'm also going to get a text sent to my phone. So as you can see immediately as I reach 0.1, it's going to tell me deflection has exceeded the selected limit. it's going to tell me to inspect the structure. Okay, so that's basically the front panel of our program. The next video we'll talk about the block diagram. So one additional thing about the front panel is that you can specify which types of text message alerts you'd like to receive. So if you don't want to receive an alert if the shear stress is exceeded, then you can just turn this off, and the alert system will still show an alert on the screen, but you won't get the text. And so now I'm going to talk in depth about the block diagram. So we're going to go over to the block diagram, and as I showed you in the previous video, here I'll show you again. Here's the navigation window, so we can see the entire program. I'm going to start here, work my way down here, and then kind of work my way through the program. So let's start right here. Close this. Okay, so here we have the DAC assistant, and this is the virtual instrument that receives the information, the digitally converted information from the DAC box. And in our program, in our apparatus, we're using a compact DAC with the NI module 9235, and that one is just specific for strain. And it's in a quarter bridge configuration. And so if we open the DAC box here, we're going to see the properties. So it takes a second. We're going to open it. Okay. So here we have the properties of the DAC box that we specified. So here we have different channels, and if we go to details, we're going to view which channel. So right now it's in 4, 5, 6, and 7, and those are just specified on the hardware. Okay, so we're going to go back, and then so for each gauge, the gauges that we're using have a gauge factor of 2. And a gauge resistance of 120 ohms, and we selected quarter bridge configuration. And then so here is kind of an important part. This is where we decide how often we want to take samples and what our sampling rate is going to be like. So we want to select continuous samples because we want the program to keep running whenever we run the program. We just don't. You could also specify to just take a certain number of samples and then stop, but that's not what we want to do. And so here we select the samples to read and the rate at which it's going to read them. So I played around with this a little bit, so kind of gone back and forth between 100 and 1,000 samples to read, keeping the rate at 1 kilohertz. The difference between 100 and 1,000 is that I ran into a problem when I kept it at 100 before with a buffering problem, which means that the program is taking in data faster than it could process it, and then so the data was kind of backing up, and it was running out of the buffering space. And then I think I dealt with that problem in the program, so instead of going 1,000, I went back to 100, and it seems to work well now. And that also gives the modeling portion of our program just a better image. It looks clearer and it's smoother. Okay, so we're going to do that. It's going to configure the DAC now. And we're just going to wait a second for that to happen. Okay, we're all set. So now if we go down a little bit, the output from the DAC just comes out of the data portion, and it's dynamic data, which is specified by blue lines, whereas orange lines are numerical values, and purple are string. And so what we need to do is we need to convert this dynamic data to numeric data. And so all these little boxes are just kind of comments that you can put in. If you just double click, then you can type and then drag an arrow and point to something that shows a comment if you're not familiar with LabVIEW. Okay, so we convert the dynamic data to an array, and right now it's in an array with 4 columns. So in order to get each specific measurement, each specific strain measurement, we need to split it into four rows. So the first row is going to be from the first channel, which is strain gauge 0, as we see here. And then so that's going to split it into strain 0, then strain 1, 2, and then 3 is down here. Okay? And then so when we get the strain measurements, we're going to set up our apparatus to a 0 point. We're going to set this number to 0, and then we're going to set all the 0 offsets to 0. And then we're going to run the program, and we're going to see what the strain measurements are. And then once we see what those measurements are, we're going to take those and put them into the 0 offset. That way we can specify where we want our 0 point for our experiments to be. And so I'm just going to undo that, so I put it back. Okay, so that'll take whatever value it's getting and subtract this value so that it'll put it at 0 where we want it to be 0. Okay, and then here we go down and we're going to have an indicator here. So when I double click on this, it's going to show where it is in the front panel. Okay, so as you can see, this is strain 0. This is that indicator. If I double click on this again, it's going to take me right back to the block diagram. Okay, and then so since we want this number in, well, when we want to see this number, we don't want to see 0.000, etc. We want to see it in micro strains, so we just multiply it by 10 to the 6th. And so the way LabVIEW works, I should have explained this before, is that it connects different functions or different tools that are virtual instruments by these wires. Okay, and then so you can connect wires to different things. Okay, and then so it just follows kind of a path. So it's going to come in here, come down, get converted to numeric, come in here, get the row specified, come in here, subtraction, etc., etc. And then so as I said before, this is the indicator. And then so we're going to go over a little bit. And then so this line is the strain value. And so then what we're going to do is we're going to convert that strain using this mathematical formula, which is just basically comes from a simple beam. You can go from strain to stress, from stress to moment, and then from moment to force. And then so we're just following this equation, which we derived from those relationships. And so what you see here is basically just a lot of math and all these things. So it's going to get multiplied by the modulus of elasticity. So strain times modulus of elasticity here. Then we multiply by the base. Then we're multiplying by the height cubed. Okay, and then we're dividing by this thing, which is 12 times L minus X times Y. Okay, and then what's going to come out is the force value that is being calculated from the measurement from strain gauge 0, and then so on and so forth for the other strain gauges. So here we have force 1, which is force value calculated with the measurement from strain gauge 1. Okay, so then what we're going to do is we're going to average these values together. Since they should all be the same, since we're taking measurements at the same time, the force that's applied is the same. So we're going to average these to get the most accurate force value. So we add them all together, and we divide by 4. And here we have an indicator which is showing the current applied force. And here is that graph indicator that I showed you before in the front panel. Okay, and then so from the current applied force, we take that, and these wires get a little hard to follow, but I'm going to scroll up a little bit. And then so we're converting these into various other quantities that we're concerned with. So here we're converting that force to a normal stress using F times L times Y divided by the modulus of the moment of inertia, excuse me, in this portion. Then we take that normal stress, we can convert that to strain. Up here we're taking force, L cubed times F L cubed, and then we divide that by 3EI to get the maximum deflection. Again, here's the graph indicator of deflection that you saw in the front panel. In this portion, we're also taking base times the height. I tried to mark these with what the output was. So this is outputting base times height, and then input here is force divided by this base times height, and then we divide that by we multiply that by 1.5 to get the maximum shear stress, and that's how we get those four values, just using relationships that we derive from just simple static deflection equations. Okay, so in this portion, right over here, for each of those quantities that we calculated, we need to compare them with our constraint values. So here we're going to take the current maximum shear stress and compare it to, so the way this works, it says if this x, so the input up here, if x is greater than or equal to y, then the output is true. Okay, and then so y here is the allowable maximum shear stress divided by the safety factor, which is what we want it to be. That's what we want to compare the current to. Okay, so if this is true, then we go down here, and this is an AND. So as you can see with this comment, this will return true only if both this and this are true. And then so here we have the enable alert system, which is that button you saw, I'll show it to you, in the front panel. Okay, so we have this enable alert system, and so right now it's on, which means it's returning true. If it's off, then it returns false. And we have those down in the other ones for the other comparisons as well. So if both of these are true, this is going to become true, and it's wired to a case structure. Okay, so here is this giant case structure. So here's the question mark. So if this is true, then this is, so what is ever in here is the true case, and if it's false, nothing's going to happen. Okay, so we'll go back to the true case and explain that. Okay, so we're going to call this outer one just C1. Okay, so once we're into this loop, this is where things get a little complicated. This while loop is going to start executing, and the way a while loop works is it's similar to other programming languages. If something is true, or while something is true, excuse me, this loop is going to keep running. Just so iteration. So whatever is in here is going to run each time, just every time while something is true. And then so here we go down in here. So when the program first starts, it's going to. Here, let me explain this in a better way. So when the program first starts, this value is 0. Okay, and the way the shift register works is each time the while loop is executed, the shift register counts it, and so that number is right here. So each time it's executed, the first time 0, so it's nothing, and then the second time 1, 2, etc. Okay, and then so we're going to take that value and add 1 to it. So the first time it goes through, we're going to have 0 plus 1. Which is 1, and then if that equals 1, then we want this to be executed, which is where the alert will actually happen. The reason we do this is that we don't want the alert to just keep running and just keep displaying messages and send 1,000 text messages to your phone. We really only want it to send 1, so that's why we do this method. And another thing that we had to do is that each time we run the program, if we don't stop it and then restart it, this shift, the beginning of the shift counter is going to remember what it was the last time. So that's why we have to reset it to 0 each time we run the overall program. And what you see here is a while loop that encloses the entire program, and that's so the program just keeps running continually when we press run. Okay, so back down here. So for the first time that the while loop's entered, this will be true, since 1 plus 0 is 1, which equals 1, of course. So this is true, and then we go into this case structure, this big one, C2, and this is the true case, and the false case, again, contains nothing. Okay, so what this VI does is it just automatically displays a message if it's run. So right now we just have the message set up to display the shear stress, because that's what we were comparing over here. We were comparing shear stress. Okay, so we take that, and that's what the message is going to be. And so in this additional case structure, which is within C2, we have this enable text alert, so we could turn on or off the text alert based on whether or not we want to turn it on or off. And that's wired to this case selector. So again, true and false contain something. And so here is how we send a text message. So what we do here is basically we start here. So this is going to, I'll open this is the really useful tool called the help. So it's going to explain each one of these things. So this is the VI that opens a handle to a server. This is how you access the internet, basically. And right here is a VI that specifies who the message is going to. This specifies what is in the message, and this is going to send the message. And then here we're going to close the connection because we don't want to leave it open. Okay, and basically what's going into each of these things is just various specifications that you need to put in, such as your email, your password, what the server is. I had to use a concatenate strings here to put together what the actual server name is. And you can find all this method online if you just search can LabVIEW send a text message. And right on the National Instruments website, they have a really good explanation of how to do this, and they also have a quick little VI that you can open and look at. Okay, and then so here, this is what we select as the message. Since it's shear stress, of course we want to say shear stress so it's the selected limit. Okay, and then so down here, we just have the messages for the other cases. So this is the deflection case. Okay, and it follows the same exact procedure. So it'll only send it the first time, and you can turn it on or off. Basically the same thing. And the comparison works in the same way. With the first conditional statement, and then the second one, depending on whether or not you want to turn the whole system on or off. Okay, and then we have the third and fourth cases, which are for, this one is for, let's see, this one is for strain, and then down here it should be for normal stress. Okay, and so we're going to go back, way back here, back to where we got the force, if you remember. And so down here, this portion of the program is where we are going to specify where we want to write the measurements to, because it's important to be able to export the measurements and the readings that we're getting to a file, so we can analyze them using another program or export them to MATLAB, etc., graph them. You could also do that in LabVIEW if you wanted, but it's also nice to be able to send them out to a file. And so here is, if you follow this blue line, this is the input. So this goes into signals, which you can see up here. I forgot to have this open. Close this. Okay, and so each one of these, this is kind of gathering all the signals, or all the measurements from the various things and converting them into one dynamic array. Okay, and this is the order of the columns that are going to be put into the Excel file. So the first column is applied force, the second column maximum deflection, etc. Okay, and then here, this is where we specify what the file name is that we want it to be saved to. I'll show you where this is on the front panel, as you can see down here. Excuse me. And so we're going to go back here. So we specified the file name, and here it's going to tell us where the file is being written to. And here again we have another way to specify whether or not we want to write to the file or not, with a simple click of a button, so we can turn it on or off, which is really useful, because you don't want to always be writing to the file. Okay, so down here again, this is the force coming out. So the force value comes out over here, okay? And here, what we need to do, since we only have a certain number of images to select from in our database, and each one of those images is at an interval of 0.1 pounds. So in SolidWorks, what we did is we created an FEA analysis of the same beam, applying different forces. So we started at 0, and then 0.1, 0.2, 0.3, etc., all the way up to 7.0. And then we went to negative 1.0. So we have a range of about 80 images to select from, which is how we're able to get such a good image of what's actually happening. Okay, so what we need to do in order to be able to display the images is we take this force value coming in and we're going to round it. Okay, and the way this works, so what we want to do, since it's a small, pretty big number, so we want to divide it by a certain power. So we divide it by this power, and then LabVIEW has a tool to round it to an integer. You can't, in LabVIEW, there's no way to specify what you want to round it to, but you can write this little code to be able to do that. So basically, we divide it by a big number, or actually a small number, so we make the value larger. We round it to 1, and then we multiply it again by that number. So that's going to give us the rounded number. And you can also find a quick little way to do this online if you just Google how to round numbers in LabVIEW. Okay, so here is just an indicator of what the rounded number is. And what we want to do down here is we take this and we go, before I'll explain that, this is kind of just a preventative measure, so that if we go out of the range of the number, so say the force is 8-pound forces, and since we don't have an image for that number, we don't want to be calling an image to be displayed. So we put the display image in a case structure and set it so that this value has to be less than 6 or greater than -1 in order for this to be executed. Okay, so we take this rounded number and we want to put it in a string, which is going to become the file path. So for each image that we have of the FEA simulation in SolidWorks, we saved it as whatever the force value is. So if the force value is 6.0, we saved it as 6.0.jpg. Okay, so here's the string. That will come out. So if the force was 1, then it would be 1.0.jpg right here. And then what we want to do is we need to convert that string to a path, which is just another LabVIEW function, so that you can call an image. I'm going to turn the help on again. And so here we have whether or not you want to enable the modeling, so that can turn it on or off this entire case structure. And so what we do is we take this path and we put it into a read the JPEG file. So this is just another LabVIEW tool that reads the file, and then we're gonna we have to draw the pixel map, and then this will also display it. So this is basically where it's displayed, and this is just the picture that's being shown. Okay, so that's basically our program here, and you can also, if you just look up how to display an image in LabVIEW, there's various ways to do it, but this is just a way that made it easier for my program. Okay, so that is the block diagram, and that pretty much concludes our video.